If not, let's go into the last questions. I think the last question is the most fun one. Oh, I see there's a question in the chat. Um, so the last question is called swap to win. You're given a matrix, a letter matrix. So you have a target string, and an helper string from S1 to Sn. Um, I assume you already read the problem statement from S1 to Sn. It's a letter matrix, because S1 can have letters going from 1 to n. So it can have, let's say, banana in the sample statement. So you will have a letter matrix. And you are allowed two operations. You have a target string. Let's say T, that's of the same size as is also of M letters. And you're only allowed two operations. So either you are allowed to find two target positions within a string. So I can find two target positions within the string and do a horizontal swap. Or I can find two vertical places within the string, within this matrices and do a swap. So these are the only two operations I am allowed. So first think about why it can guarantee us um, we can actually make our first row equal to the target with 2m total operations. Um, why this budget is only 2m if guaranteed the letters we need in this T exist in our matrices? This is the first question I ask myself. Um, I realize in the worst cases, so in the worst cases of your matrices, you have a target and this is your S1. Let's say you want to switch this G into, let's say at these places you have this letter G. And in your target, you have the letter L. So you want to switch this G with something L inside the matrices. I ask myself, what's the worst cases? The worst cases is the letter L doesn't actually exist anywhere in the matrices, but it says from the problem statement, guarantee a solution always exists. Then there must be an L exists in this matrix. Now the best case is right next to me, so I can swap directly. Or the best cases is, oh, it's just down somewhere in the same column, then I can swap directly. Then this takes one operation for free. But I have M position to actually fix. In the worst cases, how many steps can each position take? In the best cases, it's 0 step because if the letter is already matched, then it take me nothing. But if they are not matching, I can find someone in the same row or in the same column that also takes me on one. But what about even worse? I ask myself, well, what about if this L is randomly here, then how would I move? I got two options, right? I got two options, which is if the L exists to the lower left of myself, I got two routes. I either move it up to the first row and then swap to the G. So that's my row one. Or I swap myself to the right first, still in the same row, but make myself in the same column as this G, and then swap it to the top with this G. This is my row two. I ask myself, well, which one do I prefer? Then I realized I must use the row two. Because if I ever use the row one, I'm a, I'm a stupid human. I like to fix my string from the left to the right. So that basically means I should trust myself everything before the C is fixed. So if I actually follow my route 2, I would interfere with someone I already fixed because I have swapped it with this G? What if this previous places does not want this G? So I quickly realized I should not go into this route 2. Sorry, I should not go into this route 1, but stick with my route 2 strategies anyway. No matter what, I should stick to my route 2 always because it's the safest path. They all take a step size of 2, but this route 2, where I first swap to the right and then swap up with the G, will not interfere with any previous letter I have fixed for myself. They're all taking 2 steps, but never interfere with all the previous fixed spot I have taken. Then I realized that's the worst cases. The worst cases is taking 2 steps without interfering any previous answer. I can fix this G in 2 steps. Similarly, if like this G, if this L actually exists somewhere to the lower right of this G, I should always take this black route where I switch left and then I switch up. Um, I don't like going up first and then swap it because what if here it's already a match? Then you kind of ruin the match. So I don't like going into this green route, even though it's another alternative to make it work. But I could possibly delete a match here by swapping with the G. So without interfering any future possible matches or previous existing matches, I should always, if the G, the target letter, is to the lower right, I should always swap it to the left and then swap it up. So that's my strategy. I realized, oh, the best case is 0. I don't need to move at all. The intermediate best is I can find the target letter in the same row, same column that takes me on 1 operation. Now, finally, in the worst cases, I can always fix my mismatch in 2 steps without interfering future matches, without interfering existing matches. So then I realized the budget of 2M is actually a reasonable budget because for every mismatch, the worst case is I can use 2 steps to fix it. Then in total there are m spot. Then the worst case is I can use is 2m operations. I can fix all the matches. Now with answering this question, we actually quickly figure out the strategy to play the game. So whenever you find a mismatch, let's use a for loop to go left to right in your string 1 and compare it with the target. Whenever it's a mismatch, what is my strategy? I just scan linearly for any replacement letter. Scan linearly only to your right. So you have some intermediate G that is mismatch looking for L. You should only search for your right. So for future letters for L, you should not be searching back for your already fixed letters. Even if there is an L exists, swapping this L with this G will actually make your previous fixed letter ruined. So you should not be looking forward. You should always look into the future for the possible L exist. But you are allowed to always look down for the same column for and your target letter, let's say L. So you can actually search horizontally freely. And what is the runtime complexity? For that, so I realized in the worst cases, if you're looking to the future remaining letter for it now, it's all of n. Because every row you can have m letters. Horizontally, this matrix is n times n, so it's O of n. Well, if the word is as great as this, I quickly can figure, well, in the worst case, all of them, it's scanning to the linearly it fixed, then it's O of n times n. Even if it's two words, everyone I look horizontally, it's n times n. And in this question, n that large, I think it's 10 to the power of 3. Oh, I'm very happy. This is 10 to the power of 6. I think this question is given me for free. And then I quickly realized, well, what about this cases? What if there's no matches in the row and in the columns? Then I basically have to search for all the spaces. I basically need to search for all the letter matrices to actually find my existing letters. So in the worst cases, this add complexity to it. It's um so it's m times I have m letter. What if m every one of the letters in the worst cases I have to scan through all the matrices to find the letters I need to swap to? Now this gives me trouble. This is 10 to the power of 9 or even bigger. Now the problem is, oh, in the third world where this number actually does not exist, how can I look up where my target letter is without scanning through these matrices many, many times? Then I quickly realized, oh, I can use a map. Let's map the character into the places where it exists so I can quickly into the coordinates where it actually exists in the matrices. Then in O1 of time, I can look up where it is without scanning through these matrices again. Then I can get rid of this O times N. Now this time actually meet the requirement. Now here is my code structure planning. There are T test cases, right? Now for every test cases, I should read in the dimension for my matrix, the target string, and then my letter matrices. It's one indexed. I build the location map for the second row till the last row because these are the letters I'm allowed to swap to row one. And these are my target letters if it doesn't exist in the same column, the same row. Now I create a map to map the character into where are the list of coordinates that actually store the characters so I can use without scanning through these matrices. Um, in short, it's going to be Sij, what letter you have is a map, right? And then add its coordinate. Um, and this helper function is to update this map. Because once you have swapped the letters, like if you have swapped the column um, horizontally, then the coordinates actually doesn't exist in these old places. It now exists in these new places. Same thing for the lattices, right? So this is a helper function to update whenever you did a horizontal swap, or if you did a vertical swap somewhere not in the first row. Some letters, some previous operation did this swap, and then the location for the letters is going to change. So this is a helper function to help me update this old this ij is removed from some old locations, and then you should add this ij to some new letters to locations. Um, and then this operation is helping me to pre-store the answer, the string of answers I need to print out. Now I go from basically this for loop is what I said. I go from left to right. If the current letter is the same as my target, then I should skip it. Now this is a case when is not the same as my target, then C is the letter I'm basically searching for. Now this priority 1, 2, 3 is corresponding to my gaming strategy. So priority wrong is I searching horizontally. Here the key point is j greater than k. You only to loop to the right, so you're only swap the answer to the unseen ones. And then if you find the match, you do a horizontal swap. Here you don't update the map because uh, you're not interfering with the other rows. It's only row one. So you just swap directly. And then priority two is you search for the target in the same column. Now, when this column is being swapped, you actually need to update your functions because now see this swap the lower row is receiving a new letter. if this letter is ever being used in the future for somewhere back here, you can use it. So let's update the information and do the swap accordingly. Now finally is if it doesn't exist in the row or in the columns, then we have this pre-stored map. And then you can do O1 lookout for, oh, where does it exist somewhere else in this map? Now, when they're not the same, we follow the strategy based on where is it located at. Is it in the lower left or up lower right? Then you do the swap and update the positions accordingly. Um, and that's all I want to talk about for the solutions. Any question? I think this round of question is especially hard for implementation. It's easy to come up with a strategy to, as a human, to give a solution to the problem statement. Implementation wise, it's a little bit hard, especially for the this one, the binary ones. Even if you find the patterns, it's hard to think of how I transform the binary back to the original value, applying the mod rules. The first one I think is just a math problem, but you might miss the point where you should best sort them accordingly and find the corresponding places in the partition group. And that's all for the bronze level. Thank you everyone for coming.